bottom of page 3, we're still in section 17.1, looking at thermochemistry. So heat capacity. The amount of heat that's needed to increase the temperature of an object by exactly 1 degree Celsius is referred to as the heat capacity. And yesterday when we were talking about joules and calories, it was the amount of energy that was needed to raise 1 gram of water by 1 degree Celsius. The heat capacity of an object depends on its mass and also its chemical composition. So the greater the mass of the object, the greater its heat capacity will be. So a massive steel cable, like on this bridge, would require more heat to raise its temperature by 1 degree Celsius than a steel nail with a very much smaller mass compared to a steel cable. So even though they have the same chemical composition, obviously the one that is more massive would require more energy or more heat to have a temperature change occur. The specific heat capacity, sometimes it's just called specific heat, of a substance is the amount of heat that it takes to raise the temperature of 1 gram of the substance by 1 degree Celsius. Water has a very high specific heat compared to other substances. Metals typically have low specific heat. That should be capitalized. So water is unusual for its molar mass. It has very high specific heat capacity, but that's one of the reasons why we see it as a liquid at room temperature, where other objects of a similar molar mass evaporate into gases. So looking at it compared to a lot of these other items, like liquid water has one of the highest specific heats, and then ethanol, ice, steam, chloroform, aluminum, iron, and silver. So those will, the ones at the bottom will all turn to a liquid relatively easily if you add heat. It takes a lot of heat to raise the temperature of water. Water also releases a lot of heat as it cools. So the water in lakes and oceans actually absorb the heat from the air on hot days, and then they release it back into the air on cool days. And so this is what gives us moderate climates in the coastal areas. Oh, it went back because of the next screen. It was capitalized on this screen. See that? All right, let me make that better here. All right, so if you look at this weather forecast here, Palm Springs 119, Blythe 118, Barstow 115, Bakersfield 109, Death Valley a nice 125. But along the coast, Santa Barbara 80 degrees, San Francisco 78 degrees, San Diego 74 degrees. So we have the water there to help absorb heat on hot days and to release heat on cooler days. So you end up with a more moderate temperature year round. And then areas that don't have a nice large body of water, there's a lot more fluctuations in those temperatures at different times of the year. Here's a real life application. If you are looking at Hawaii, where they have volcanoes that are active and they're right next to the ocean, heat will flow from lava here to the surroundings until the lava and the surroundings are at the same temperature. We know that, we learned yesterday that objects that are in contact with each other, the heat will travel from the warmer object to the cooler object until they're at the same temperature. So if we have lava flowing down into the ocean, air has a smaller specific heat than water. Why would the lava cool more quickly in water than in air? The reason why is that water requires more energy to raise its temperature than the air. So if the lava is in contact with the water, it loses more heat energy than the lava that's in contact with the air. So it'll cool more quickly when it comes in contact with the water, because the water is capable of taking in that heat at a much greater rate than the air is able to. And there's some pretty unique lava formations that occur when lava does cool in water. Sometimes it forms like almost, they're called like pillow lava. So it's kind of an unusual form. All right. Another example dealing with food. When a freshly baked apple pie comes out of the oven, the filling and the crust are at the same temperature, but the filling is mostly water. A lot of fruits have a really high water content. So the fruit inside, the filling, would have a higher specific heat capacity than the crust would. So the filling has the ability to hold on to that heat at a much better rate than the crust will. The crust will cool off much faster because it doesn't have all that water content to hang on to it. So the filling has to have a lot of time in order to give off that heat. So this release of heat is why you have to be careful not to burn your tongue on that filling when the crust has already cooled because of that high water content. If you've ever tried microwaving something that has a couple like vegetables and meat, usually the vegetables are like burning hot and the meat's kind of because the vegetables have a high water content. So what a microwave does is it excites the water molecules in your food, and so the higher the water content, the hotter it would be. All right, to calculate specific heat is given a capital C in our formulas. You divide the heat input by the mass of the substance, and you also have to take into account the temperature change that has occurred. We saw Q as a variable yesterday, and that's the heat. It could either be described in joules or it could be described in calories. We do need to take into account the mass, and that would have to be measured in grams. And then the change in temperature would be the final temperature minus the initial temperature, and this time we're looking at it in degrees Celsius. We're not dealing with gas laws, so our temperatures are in Celsius for this type of equation. All right, on to page 5. All right, so we're actually going to utilize this formula here, the C equals Q over mass and over the change in temperature. We do have a reference sheet for chapter 17, so it'll be right after our previous reference sheet, chapters 14 through 16. Okay, so it says the temperature of a 95.4 gram piece of copper. So that is our mass. If it gives us a value in grams, that's our mass. It says this piece of copper increases from 25 degrees Celsius to 48 degrees Celsius. So that's our change in temperature. For change in temperature or any type of a change, you always do the final minus the initial. So we're going to go 48 minus 25. And so we'll figure out what that difference is in a minute. And it says that the copper is able to absorb 849 joules of heat. So we're going to figure out what is the specific heat of copper. So that's what we're solving for, is that capital C. As we go 48 minus 25, that is a temperature change of 23 degrees Celsius. So now we have all of our variables. The formula that we're using for this is C equals Q divided by M divided by the change in temperature. It's important that anything that's on the bottom, we put that division sign in front of. So our Q goes on top, the 849 joules. Our mass of 95.4 grams goes on the bottom, and our temperature change of 23 degrees Celsius goes on the bottom. It does not, because that was just for the gas laws we had to deal with in Kelvins. For this one, we don't have to do any temperature conversions. Yeah, it actually needs to be in Celsius. All right, so to plug this into our calculator, we're going to go 849 divided by 95.4 divided by 23. Our labels here, we have joules over grams, degrees Celsius, so it seems like we have a lot going on. As we look back at significant digits, each number that we were given in our problem had 3 digits. So we can keep where the 3, the 8, and the 6 are at. As we peek at what's going on to the right-hand side of that 6, we see it's large enough to cause us to round up. So it becomes 0.387. And there isn't a better unit that summarizes all this. Specific heat is measured as grams or joules per gram degree Celsius because it's describing how much energy it takes to increase 1 gram of a substance by 1 degree Celsius. So that's why our unit ends up in that way. So there isn't an easier abbreviation for that. This is listed on our reference sheet, so it does tell you the units that you're looking for. All right, another example. Here we're solving for something different. It's asking us to find the mass. So we're going to manipulate our equation so that we're solving for mass instead of specific heat. So it says the specific heat of ethanol is 2.4 joules per gram degree Celsius. So they are giving us C. That is the specific heat. A sample of ethanol absorbs 676 joules of heat. That is our Q. Anytime they tell us heat, that's telling us our Q value there. The temperature rises from 22 degrees Celsius to 64 degrees Celsius. So that's going to tell us our change in temperature. We're going to go our final temperature, 64 degrees, minus our initial temperature, 22 degrees. And it asks us, what is the mass of ethanol in the sample? So we're looking for M here. On a reference sheet, we have our formula solved for any one of these variables, so we can see that mass equals our specific heat, or no, our heat, Q, over our specific heat, and over our change in temperature. As we're looking at all of our units, we have our heat given to us in joules, our specific heat is given to us in joules per gram degree Celsius, and our temperature change is also given to us in degrees Celsius. So we're going to have some things that are going to cancel each other out here. Our change in temperature, we had 64 degrees minus 22 degrees, so the overall change was 42 degrees Celsius. All right, so we can actually plug it into our formula now. Our heat is 676 joules, that goes on top. Our specific heat, or C, is 2.4 joules per gram degree Celsius. And our temperature change is 42 degrees Celsius. So any number that's on the top, we're going to multiply. We just have one number. Any number that's on the bottom, we're going to divide. So every number on the bottom is going to get a division sign in front of it. So 676 divided by 2.4 divided by 42. You have to use a division sign in order to keep that as a denominator. So we get this nice long number. Looking at our units, I just want to show you that the units will work out. So our units are, we have joules over joules per gram degree Celsius, and then there's a degree Celsius here from our actual temperature change. When you have something that's under 2 division signs, that means that this actually belongs as a numerator. So it becomes joules grams degree Celsius over joules degree Celsius. So we can see that our joules are going to cancel out, and our Celsius is going to cancel out, and the only label that remains is grams. So I proved to you that yes, the units work out. It will be grams. We assume that mass is going to be measured in grams as well. Looking at significant digits, we had 2 digits for specific heat, we had 3 digits for heat, and we had 2 digits for our temperature. So the least amount of digits would be 2 digits. So our value becomes 6.7 grams of ethanol. Stuff like this, the unit analysis, takes me back to my days of teaching physics. We did a whole lot of that in physics, manipulating equations and stuff. All right, let's finish out section 15.1 by just running through some vocabulary on page 6. We don't have a physics class here.
So unlike the graphical tools that they give in previous classes, we able to just put it in the front of the fraction, that is the fraction.
You might need to use parentheses on the bottom if you're putting it in as a fraction. What you could do is run it through and see what it would take to get this answer, to verify how to plug it in correctly. All right, our important vocabulary so far between yesterday and today for section 17.1. So we talk about energy. Energy changes occur as either a heat transfer, always going from a warmer object to a cooler object, or if we have work being done, or there's a combination of heat being transferred and work being done. If there's a chemical change, or if we have a physical change, like going from evaporation or freezing or melting, the energy of the universe remains unchanged, even though we see these changes of energy occurring. That energy is neither lost nor gained. The heat capacity of an object is relying on its mass and also its chemical composition, and water has one of the highest heat capacities. Thermochemistry is what this section was about, and it's the study of energy changes that occur both during chemical reactions and also during these changes of state. Within the chemical bonds of a compound, there is chemical potential energy. And then heat is shown as a lowercase q, and that's the energy that transfers from one object to another because of a temperature difference between those objects. All right, this system is where we're focusing our attention when we're trying to make judgments as far as if it's an exothermic reaction or an endothermic reaction. We're focusing on one part, and then everything that's around that system would be referred to as the surroundings. We also talked about the law of conservation of energy yesterday. It's in the same, it's one of the same laws of thermodynamics as the law of conservation of mass. Mass cannot be created nor destroyed, it just changes form. Same thing with energy. It cannot be created nor destroyed through a chemical or physical process. And then the two types of processes that we learned about yesterday, an endothermic reaction or an endothermic process, heat is going into this system, so it's absorbing heat from its surroundings. And an exothermic reaction or exothermic process, heat is exiting the system, so it's releasing heat to its surroundings. So in an endothermic process, the temperature of the surroundings drops because that heat is being transferred into that object. So that's how ice packs work. An exothermic reaction, heat is being released into the surroundings, so the temperature of the surroundings increases. All right, the heat capacity is how much heat it takes to increase the temperature of an object by 1 degree Celsius. So no temperature conversion is needed. We just keep it as Celsius. And then specific heat, it just takes one additional layer. It's how much heat is needed to increase the temperature of 1 gram of a substance by 1 degree Celsius. It can also be referred to as the specific heat capacity. Energy is always conserved. If the energy is increasing within a system, that means that the surroundings have decreased. If the energy is decreasing in a system, that means that the surroundings have increased. And that's what we need to know for section 17.1.